So suppose we had a graph of displacement versus time, and we wanted to look at the slope of the tangent line at point A. So we would really be looking at this point A, which perhaps has an x-coordinate of little a, would be the velocity. And that would be the velocity as the limit as h approaches 0. So if we picked another point and had a coordinate of a plus h here, limit as h approaches 0 of the displacement at a plus h minus the displacement at a all over h. Now consider looking at the cost to produce some material, a widget perhaps, and we have a graph, looks very similar, and we want to find the slope of the tangent line at point A. Well, this time we could interpret this as a marginal cost. And the formula looks pretty much the same, except now we have a cost function instead of a displacement function. And then we could also look at the population of bacteria over time. And again, we can look at the slope of the tangent line at point A, and we could find the growth rate as the limit as h approaches 0 of the population at a plus h minus the population at a all over h. So we can see that these are all rates of change. They're all really the same thing. So this idea of finding the slope of the tangent line at a point allows us to solve many different kinds of problems. So now let's take a look at a graph of y versus x now. So we'll just look at a normal function, y equals f of x. And again, you can use this idea for any of the other problems we've talked about. And we have 2 points, A and B. And we'll say that A has an x-coordinate of x1 and B has an x-coordinate of x2. And then I'm going to define a couple things here, this delta x and delta y. So first, let's look at the coordinates of A. That'd be x1, comma, f of x1, and the coordinates of B would be x2, comma, f of x2. And then delta x is that distance between the x-coordinates. So this distance right here, that's what I'm calling delta x. And so that would be x2 minus x1, and we have a name for that. We call that the increment. And then delta y would be f of x2 minus f of x1. And so the average rate of change, which is, if you remember, analogous to finding the slope of the secant line between 2 points, that would be delta y over delta x, or f of x2 minus f of x1 over x2 minus x1. So that's just your normal slope formula. This thing, by the way, is called the difference quotient. Now we know that if we want to find the instantaneous rate of change, then we take the limit as delta x goes to 0 of delta y over delta x, or written more explicitly, we could say the limit as x2 approaches x1 of f of x2 minus f of x1 over x2 minus x1. And remember that we also had another way of writing this in terms of h, where we let h goes to 0. Either way works. They're both really telling you the same thing. So let's look at an example. Suppose we have a chemical reaction that consists of this gas, nitrogen dioxide, that's decomposing. So we're going to heat nitrogen dioxide in a closed container. And we have a table of values that shows the time in seconds and the concentration of nitrogen dioxide in moles per liter. If you're not familiar with what moles are, it's just another way of counting things. It's kind of analogous to a dozen. You would say a dozen eggs would be 12 eggs. Well, a mole of particles ends up being a lot of particles. It's 6.02 times 10 to the 23rd. But we don't need to worry too much about that here. So we have this table of values, and then I'm going to plot this. So we have concentration on the y-axis and time on the x-axis, and we see something that shows it starting here at 0.0150 and then slowly decomposing. And that's happening according to this chemical reaction right here. So another thing I can do is maybe draw a nice smooth line through these points, just so we can kind of get a sense of what's happening. And I want to find the average rate of the reaction from t equals 0 seconds to t equals 100 seconds. So remember, average rate, that's something like finding the slope of the secant line here. And so the average rate would be the concentration at 100 minus the concentration at 0 divided by 100 minus 0. Remember, the average rate is always something that we look at over an interval of time. And so I can plug in some numbers here. So I can just look these up in the table. We see that the concentration at time 100 is 0.0093. So I plugged that in, and the initial concentration was 0.0150 over 100 seconds minus 0 seconds, and we end up getting negative 0.000057 moles per liter times second. And by the way, you'll notice if you look at this in chemistry, chemists tend to prefer having positive rates rather than negative ones. So a chemist might actually define the average rate as the negative of this, which would then make it positive. But we're not going to worry too much about that. The point is, average rate, which is something over a time interval, is analogous to finding the slope of a secant line. Now let's look at the instantaneous rate of reaction at t equals 40 seconds. So remember, instantaneous rate, that's something that happens at a point in time. So the instantaneous rate will be the limit as delta t approaches 0 of the change in concentration over the change in time. Well, normally what we would do is we would plug into that formula for the limit, but we have a problem here because we just have a table of values. We don't have a function to work with. So instead what I'm going to do is I'm going to make a little triangle right here, and this is a triangle that has as its hypotenuse what would look like the tangent line here. I'm just kind of making my best guess. And then using the other two sides of the triangle is what we had before is like a delta x and a delta y. Although in this case it's a delta t and a delta c. So I'm going to use these sides of the triangle to try and approximate this and see if I can come up with an instantaneous rate. So what would this look like? Well, if I were to look at the delta c, so that's the numerator of this, I have 0.0104, so that's about right here. I'm just kind of guessing about what that would be on the axis here. Minus 0.0126, that would be up here, about that y value there. And then 60 minus 20, so that's just these values here. Here's my 60, and then over here, here's my 20. All right, so this, again, I'm using the approximation symbol here because this is not quite exact here. I'm sort of reading off of a graph, but it's my best guess at what the slope of the tangent line might look like. And so when you compute this, you get negative 0.000055 moles per liter times seconds. So the important point here is that the instantaneous rate is something that happens at one point in time, and that's analogous to finding the slope of the tangent line at that point.